Okay, we're now going to look at the three-dimensional version of the Sierpinski gasket, and for the most part, for the rest of the class, everything is going to be in three dimensions. So how do we go to 3D? Well, one way is to create a tetrahedron instead of a triangle. So here's four vertices for a tetrahedron that are. The way I got these is if you start with a unit sphere, okay, a sphere centered at the origin with radius 1, you can find 4 points that are equally spaced along that, along on the surface of that sphere, and then connect them with line segments, and you'll have a tetrahedron. It's a little tricky, but if you start with 1 at say x equals 0, y equals 0, z equals -1, you can then find where to put a plane that then we'll have, which will be at 0.3333 for all three of the other points. They form a triangle, and in that plane z equals 0.333, and you can now put an equilateral triangle in there, and you'll have a tetrahedron. Now, one way to get this 3D version would be to simply take each face and apply exactly what we did in 2D to the faces. That's not very interesting because it's just each one is just kind of going to look, all you're doing is going from 2D to 3D, and you're really doing a 2D problem, since you're going to do the subdivision or the random algorithm on each face. That's not very interesting. So let's do a true three-dimensional way of looking at it and say, okay, what I'm going to do is now, instead of subdividing each of these faces, what I'm going to do is actually remove a tetrahedron corresponding to each of the vertices. So if you look over here, what I've done is take the bisectors again. Okay, so here's the bisectors on this front face, the bisectors over here, and on the bottom and behind there, we're doing the same thing. Well, if I connect those bisectors, I've formed a littler tetrahedron, a smaller tetrahedron, corresponding to each of the four vertices. So I've formed four tetrahedrons. Here's 1, 2, 3, and there's sort of the fourth one back there. Each of which have, each side, if the full length was 1, each side is now length 1/2, and you could figure out, the area of each of the four subtetrahedrons, and you've removed this space in the middle, and you once more can show that this is a kind of an interesting fractal, because what you've done now is every time you're removing a part of the area, but you're also increasing the length of all the surfaces. So if you add up either all the surfaces instead of the perimeters, the surface area is going up every time, but the volume is going down. So this is in fractal dimension, this is somewhere between a 2 and 3-dimensional object, and later we'll use that as an example and show you what its fractal dimension actually is. Now the code is almost exactly the same as it was in 2D. We'll consider the recursive form. So what we do is, instead of dividing triangle, we divide tetrahedron, and each time we divide the tetrahedron, we do a subdivision into 4 smaller tetrahedrons, subdivide those until we finally get down to the number of subdivisions that we specified, and when that gets down to 0, we simply render the tetrahedron. Now, so far it looks pretty good. Every time what we're doing is putting 4 vertices into our array by pushing them onto that array, instead of 3 vertices as we did with the Sierpinski 2D gasket. The problem is, when we try and do the rendering, things get a little bit strange. And the reason is that when you're doing the subdivision, you're not taking into account where in space each of those tetrahedrons, or the faces of those tetrahedrons, is actually located relative to the others. You're just doing it within the order that your particular subdivision routine says to do it. And if you simply do a render on all of those triangles that you've created from all of these little tetrahedrons, you'll get something that will look pretty odd, because it's not taking into account where they are in 3D space. So the program's kind of almost right, but not quite this. So if you look at what you get this, and look what's happening. It sort of looks like a tetrahedron and a Sierpinski Sierpinski tetrahedron subdivision. But notice these little green guys. What I've done here is use uniform variables to color each face a different color so you can see the difference. So the back face from you, this vertex over here is the one closest to you as the viewer. So you see these three faces, and you should only see this back face where where space has been removed and there's nothing between you and the back face. So the green should be this face that's furthest from you, but look, it's showing up as little green triangles here in front of the ones that geometrically are actually in front of it. And why? Because we've not taken into account where things are actually located relative to the viewer. Or very simply, we haven't done hidden surface removal. This is what we really want. We want to see only the green in the back where it's not hidden by the red or the blue or the black. This is the correct display over here on the right. So we need to add some sort of hidden surface removal to what we've been doing so far, and that's standard whenever we're doing 3D problems. So it's easy to go from 2D to 3D, you're just going from Vec 2s to Vec 3s, but you have to add this one extra step. And it turns out that step is sort of built in. So let's look at hidden surface removal by a particular algorithm which is built into all versions of OpenGL. So here's the idea. Here's a viewer. Here's three objects out there in space, and you want to take into account that object A is closer to the viewer than object B, and if these are opaque, A should block out at least some of B and C as seen by this particular viewer. So obviously it does depend on where the viewer is located. Now, one way of doing this is to try and think of some sorting routine that we'll talk about later that says, oh, if I paint B and C, I can paint B, A over them, or render A over them at the end by figuring out the proper order. Turns out there are some issues with that, and it's not the algorithm that works best in real time. What works best in real time is an algorithm called the Z-buffer algorithm, which works well with what we're doing, because what we're doing is processing an object at a time. A strategy like a painting algorithm sort of assumes you can compare all these objects to each other and you have them all available. But that's not the way a pipeline renderer works. A pipeline renderer says, whatever object you give me first, I'm going to render it. Next object, next object. There's no sorting or ordering associated with it. Well, the way that the Z-buffer algorithm works, and we'll talk about it in more detail later, is that it stores information about where the depths are, how far things are for the viewer, as it renders each object. So I have that information, I store it in an extra buffer which is supplied with all versions of OpenGL, including WebGL, called a depth buffer, and as I render new objects, I can compare with what's in a depth buffer to see if there's something I've already rendered that's in front of me. Well, from the user's perspective, all you have to do is enable it, and it's called a depth test, and all you need in your initialization is GL enable and give it the parameter GL depth test. And the only other thing you have to do is clear the depth buffer each time, because each time you do another render, you want to start with that thing cleared, because the objects in an animation could be moving relative to each other in space. So rather than just clear the color buffer, you're clearing also the depth buffer, and you're using the OR to say you want to clear both of those each time. So it's basically two lines of code have changed, and we're automatically doing hidden surface removal. Very easy to do, really doesn't slow you down at all. And this is just a reminder that we're working now with volumes instead of surfaces. The code is all in the text for subdividing tetrahedrons and then rendering all the four triangles that are the surface of each of the tetrahedrons at the end. All of the code is in the text. It's also online on my website for Chapter 2. The fourth version of Gasket is a version that does exactly this with the hidden surface removal. And here's just again another little picture of that showing what you should get. And this really does show sort of the volumetric elements with hidden surface removal being done correctly.